Hi everyone, in this tutorial we are going to talk about single stage amplifiers. Okay, and specifically we are going to talk about CMOS Common Source Amplifier. So let's begin our discussion. First of all, what is an amplifier? An amplifier at this level can be thought as a black box, okay, which when applied with an input signal of a low magnitude, okay, it is going to give an output of this output will be a signal which will be similar in shape to the input. The only difference will be it will have an increased magnitude. So that is what is called as an amplification. Okay, amplifier just increases the magnitude of the applied signal. It doesn't change the waveform actually. So mathematically we can write it as, if we call this as Vin of t, if we call this as V naught of t, then your V naught of t, okay, dV naught of dt, if we change in output voltage is going to be some constant k, where k value into Vin of t, where this k value is going to be very much greater than 1, approximately of the order of 1000 or 10,000 and so on. Okay, so this is what is an amplification. Suppose if I choose my Vin of t as a sine signal, sine omega t, my output will be k into sine omega t plus phi. What is this phi? This phi is a phase shift. Okay, we are not bothered, we don't want the signal to be starting at the same point. Obviously this is a system and this is a kind of circuit, and every circuit will have certain delay. That delay is going to produce a phase shift. Okay, if you apply a signal of this sort, what you may get is a signal of this sort. Okay, it is nothing but this signal delayed by certain amount. So this is the phase difference which we have mentioned. So phase difference is not important. What is important is this output signal should have a gain. Amplitude of this output signal should be very much higher than the amplitude of your input signal. This is what we expect from an amplifier. So mathematically, as I have already said you, amplifier can be represented by this linear equation, that is your V naught of t should be equal to some constant k into Vin of t. So this is the mathematical model of your ideal amplifier. So generally we implement this how are we going to implement this amplifier? We are going to generally implement this amplifier by using our active devices like BJTs, FET, MOSFETs, etc. Okay, so what we know about these devices is these are non-linear devices. Okay, but what we want is a linear equation of this sort. What is meant by non-linear equation? Okay, an equation of this sort, okay, t plus alpha 2 into V square of t plus so on. Okay, so this is what is a non-linear equation. Then how are you going to convert this non-linear equation to a linear equation? Okay, what approximation we do in this kind of problem is we choose Vin to be very less in magnitude of Vin. We choose a magnitude which is very less than 1. What happens when you choose a magnitude less than 1? Let me suppose if I take a magnitude to be 0.1, what happens is this square term 0.1 whole square is going to give you 0.01. The value of 0.01 is very much less than 0.1. So in other words, you can discard this value when compared to this value. So this is how we how we are going to approximate our nonlinear behavior in order to get an amplifier out of the nonlinear elements. So when we when we expect that means when we assume V in of t is very much less than 1, what you will be getting is an equation V naught of t, which will be equal to alpha naught plus alpha 1 into V in of t. You have, by assuming V in to be very much less than 1, you have deleted these terms, so you are left with only this equation. This alpha naught is nothing but a DC voltage. This can be easily eliminated by using certain coupling capacitor. Ultimately, what is the relation you are going to get is V naught of t is equal to alpha 1 into V in of t. This is what we wanted. We wanted a linear equation, and here we got the linear equation. What approximation did we choose? We made this approximation. That means we choose the magnitude of V of t very much less than 1. Okay. So let us see how can we approximate MOS to be used as an amplifier. So your MOS, particularly NMOS, I'm talking, symbol of NMOS is like this. This is going to be gate, this is drain, and this is source. Let us look at the characteristics of this NMOS. Okay, so this NMOS, if output characteristics are plotted, VDS versus ID, that means we are giving this voltage, GS voltage we are applying. Okay, we are seeing this output, and we are also calculating what is the current flowing through this. So what you are going to get is the characteristics are going to be like this. So on. So this is for VGS1, for one value of VGS. This is for second value of VGS. This is for third value of VGS. So what is the importance of this characteristic is these characteristics can be divided into two regions. So this region where your ID is increasing with your VDS for different values of VGS, and this part where your ID remains constant with your VDS but it is varying with VGS. So this portion, that is your DID, change in ID, is proportional to change in VDS. So this kind of relation you will find in a resistor. Resistor is going to have this relation, R is equals to V is equal to IR, okay, or R is equal to V by I. Okay, so this can be V is proportional to I. The same kind of relation you can see here. So therefore the MOSFET is going to act like a resistor in this region, and this region is named as triode region. Okay, whereas when you talk about this region, you can see that this ID is remaining constant with VDS, but it is changing with your input voltage. That means you can apply certain controlling voltage, a certain voltage here which is going to control the flow of the current. That means you are able to produce a change in ID by a change in VGS. So this is also called as your transconductance. Okay, so your dou ID, or else I can say it in this way, dou ID is proportional to dou VGS in this case. So this region is called as saturation region of MOSFET. It is in this region that a MOSFET is going to show a transistor characteristics, whereas in this region it is just going to behave as a resistor. So in this region the formula, that means the relation between current and VGS is going to be given by equation ID is equal to 1 by 2 UN COX W by L VGS minus VTH whole square. Suppose from this equation I want to calculate the rate of change of ID with VGS, dou ID by dou VGS. I am going to get UN COX W by L, the square 2 is going to come out and it is going to get cancelled, VGS minus VTH. So this dou ID by dou VGS is going to give you this value. Now you can see here this dou VGS Okay, you have differentiated with VGS, again you have a term, this slope depending on VGS. But let me show you what is this VGS. If you make this amplifier, okay, if you use this MOSFET as an amplifier, then you will be applying input here and you will be taking output from here. Okay, so this input is going to be a combination of a DC plus an AC voltage. Okay, as we have assumed in the previous page, that was discussion, that to approximate this nonlinear behavior, to convert this nonlinear behavior into a linear behavior, what is the approximation you have to use, what is the assumption you have to make? This is the assumption, that means Vin of t is very much less than. So that is what we do here. This VGS, we assume it to be a sum of DC and AC. DC is a bias voltage, we are not going to change it, but AC is going to change. So this AC, it may change, but the approximation assumption what we have made is this AC value is very much less than 1. So if this is very much less than 1, then the variation of this value with this AC voltage can be thought of as that means this value hardly varies with your AC voltage, so therefore this value can be thought of as a constant. So I will represent this constant by GM, the transconductance. Dou ID by dou VGS is going to give you this constant GM. We are assuming it to be constant. It is constant only when you assume AC is very much less than 1. Okay, so therefore by using this characteristic, by using this relation, you can model the MOSFET as okay, this is gate and this is source, this is VGS voltage, let me call it as VGS. So this is drain it. So this VGS is going to produce a current ID. So this ID is going to be given by ID is GM into VGS. So this is GM into VGS. And apart from this, your MOSFET is going to have an resistance, okay, R0, which is due to the channel effect. It is beyond the scope of this discussion. So just you remember that this is a model of MOSFET. This output resistance comes from the channel length. Okay, why? Because this equation what I have written here is actually an approximate equation. The actual equation will be Cox W by L when you don't consider channel length to be 0, then this equation is 1 plus lambda VDS. So this is the actual equation where we have approximated this equation to this value, assuming lambda to be equal to 0, but lambda generally will not be equal to 0. So the effect of this lambda can be defined as dou ID by dou VDS. When you are going to get you are going to get a constant value. That constant is I by V. I by V is nothing but your transconductance. So this output resistance is inverse of your transconductance. This is how you are going to get the resistance at the output. So this is the MOSFET model. Okay, small signal model of your MOSFET. So we have derived the MOSFET model, and let us use this model. And first of all, let us see how we can make an amplifier out of this MOSFET. So this is the NMOS you have. What I have said, that this NMOS, the relation is dou ID. A change in ID is going to be produced when you are going to change the VGS voltage. Okay, and that is going to be multiplied by VGS. Okay, so you are getting a linear equation here. Dou ID is equal to some constant K. This is gain of your amplifier into VGS. Okay, this equation is similar to this equation. Okay, V naught of t is K into V in of t, but the only difference here is, here we were talking about V naught, but whereas here we have ID. Okay, and here we were talking about input voltage, and here we have VGS. Comparing these two, So and we can find declare that in order to make this NMOS as a MOSFET, you have to convert this VGS into Vin. That means you should apply your input voltage to the gate of your MOSFET, between gate and source of your MOSFET. Okay, so this VGS now gets converted to your Vin. Okay, so this ID, we have a relation, that means this equation has ID, whereas for an amplifier we need, according to our equation, we need V0. So how to get this V0? So in order to get V0 here, you have to use a current to voltage converter. What is the best current to voltage converter, or the simplest current to voltage converter? Current to voltage is a resistor. Okay, how current to voltage is a resistor? V is equal to IR. We know this from the Ohm's law. So therefore, if you have a current, if you allow that current to pass through a resistor, you will be generating a voltage. So that is why in order to make this circuit as an amplifier, you have to allow this ID to pass through a resistor. Okay, so when this ID is going to pass through the resistor, it is going to create a voltage drop. Okay, it is going to create a voltage drop. The voltage drop across this resistor will be ID into RD, and if VDD is your supply voltage, the voltage at this point is going to be VDD minus ID into RD. So we have synthesized a simple current source, that means a common source amplifier. So simple common source amplifier is going to look in this way. It is going to have a resistor here. So this is going to be a VDD. The input voltage is applied to gate, and output is taken from drain. Okay, we'll call it as Vout, and it is grounded. So let's there are a lot of assumptions you have made during this process. For the most important assumption is V in value, we have chosen it to be a very small value. V in is a very small value. So therefore, in order to find the gain of this amplifier, if you want to know the gain of this amplifier, you have to do a small signal analysis. So in order to do a small signal analysis, we have to replace this MOSFET with a small signal model, what we have that was derived in the previous paper. Okay. So replacing that MOS, so at gate it is going to have a source here, and this is going to be the drain, and you are applying the input voltage. You are applying the input voltage to the gate. Okay, and at the drain you are having as you can see here, according to the model of MOSFET, you are going to have a VGS here and R0, which again depends on your channel length modulation, and apart from this you have a R connected to your VDD. VDD is a DC source, so therefore it will be acting like a ground for an AC signal. So here is where you are taking your Vout. So this is your Vout point. So let us analyze this circuit. This is Vn and there are no components connected here, therefore this voltage will also be Vn. So this VGS, GM VGS will now become GM into Vn. Okay, now just simplifying this circuit. Okay. Source, you will have R not connected between, and you see a source you have grounded, so there I will ground. So R0 is connected between drain and ground, and even this R is connected between drain and ground, so they will come in parallel. This is the capital R, and here is where you are taking your output voltage, Vout. So how to calculate this output voltage? Your output voltage is going to be if you assume this current is flowing in this direction, so this current flowing through this resistor is going to produce a voltage drop which is going to be equal to your Vout. So minus, actually GM is flowing in this direction and I want to assume that it is flowing in this direction, so therefore you will get a minus sign, GMVin into, what is the effective resistance? Effective resistance is the resistance of R0 in parallel with R. Okay, so therefore you got this relation. From this relation, if you want to know the gain, AV, it is given by minus GM. It is given as AVin is given by Vout divided by your VM, which is again equal to minus GM into R0 parallel with R. Generally this resistance R0 will be in the order of 100 kilo ohm to mega ohm, whereas this R is going to be a moderate value. That means it is going to be few hundred ohms to few tenths of kilo ohm. So therefore a huge value in parallel with a small value will ultimately result in a small value. Ultimately you are going to get GM into RD as your gain. Okay, so this is going to be the gain of your circuit. This MOSFET circuit is going to have a gain equal to minus GM into RD. So what all we have done here is a small signal analysis. That means assuming Vin to be a small signal. Okay, now let us do a large signal analysis on this circuit. Okay. First let me draw the circuit. It's connected to source and this is Vout. So what is meant by large signal? That means if your signal Vin is comparable, that means it varies from your between the extremes of your power supply. That means what is the extreme? My below extreme is my ground. If it flows from ground to above extreme VDD, that means it is comparable. It is flowing between these two extremes. It can vary between these two extremes. Then your input signal is called as a large signal. It is a large signal. So therefore what we are doing is called as a large signal analysis. So in this case we will assume that let us go back. First we will go back to the point where we have discussed the characteristics of MOSFET. From this characteristics you can see that the MOSFET will behave, that means it is going to act as a transistor. That means whatever the analysis you have done, whatever the gain you have got, it is going to be only valid only when your transistor is in saturation. Why? Because we have chosen an equation which is only satisfied in this saturation region. Okay, so therefore what is the condition of saturation? So the condition of saturation is this point. That means for VDS greater than this point, this value, what is this value actually? This value will be VGS minus VTH. Okay, if your VDS is greater than VGS minus VTH, only then you can say your transistor is in saturation. If it is less than VGS minus VTH, then your transistor will be in the triode region. Okay, and one more thing we know from the MOSFET, that MOSFET, it is going to be off. When it is going to be off? Well, let me write down all that equation. So your MOSFET will be off. Okay, it will be off when your VGS is less than VTH. Suppose if you are giving a signal here and that signal is, that means it is less than, it is so low that it is less than VTH, then your transistor will remain off, it will never on. For this transistor to on, that means in the on state, your VGS should be greater than your VTH, greater than or equal to VTH. And moreover, when it is on, it can be in the two different states, as we have seen in the analysis. Okay, it can be in the two different states. One is either in the triode region or either in the saturation region. So what is the condition for saturation? Your VDS, output voltage VDS, should be greater than VGS minus VTH, whereas for triode region your VDS is less than your VGS minus VTH. Okay. After getting this analysis, okay, after making a note of all these equations, we will now dive into the large signal analysis. So how to do the large signal analysis? What we will do is, this input voltage, we will start varying this input voltage right from this lower extreme, that is 0, and vary in steps. That means we are going to counter different equations, and let us see what happens if that conditions are met, and ultimately we are going to reach at this point VDD. And for this variation we are going to record the Vout radiation. So what is the Vout at this point, what is the Vout at this point? This is how you do the large signal analysis. So I need a graph for this case, so I will take a graph. So here I will plot my Vout, here I will plot my Vin. Vin is on x-axis. So let us assume I am varying my Vin, okay, this Vin, now I am tuning my Vin, and I have tuned it to a value which is less than your threshold voltage, okay, less than your threshold voltage. What happens from this condition? You can see if Vin, if your VGS, that is this gate to drain nothing but Vin in this case, because we are talking about common source amplifier. So if your VGS is less than your VTH, your device will be in off state. So when this transistor is off, that means in the first condition, that means your VGS is less than VTH, your transistor will be off. So when it is off, it means this VDD is connected to your resistor R. This resistor is connected to your transistor which is in the off state. That means there is no connection between your this point, your Vout point, and your ground. So therefore what will be the Vout? As there is no current flowing, your Vout will be, Vout is actually given by VDD minus ID into RD. As this is open circuited, no current flows, so therefore this term becomes 0 and you are going to get VDD. So till this point your output voltage will be VDD. Okay. So what happens after this point? Okay, that will be our second. That means your VGS is now greater than VTH. So when VGS becomes greater than VTH, what happens is a small current will flow through the transistor, and it is going to produce this ID. As there was no ID earlier, now ID has just started. So the ID is a very small value. That small value is going to produce a very little voltage drop across this resistor. So therefore your Vout will be slightly less than your VDD. Okay, slightly less than your VDD. It is approximately equal to your VDD. So this drain to source voltage, what will be the drain to source voltage in that case? Drain to source voltage is approximately VDD, and you have chosen your VGS. Let us assume that I have chosen my VGS is equal to the VTH of this transistor was 0.7, and now I have chosen VTH to be 0.8. So what will be my VGS minus VTH? VGS minus VTH will be 0.8 minus 0.7. It will be 0.1. Okay, and what is my VDS? The current has started. Obviously the current has started, but it is very small current that is flowing. So that current is going to produce a small voltage drop. So this Vout will be slightly less than your VDD. That means it is approximately equal to your VDD. VDD will be a 5 volt or something. Let us assume that it is 5 volt. So your VDS is 5 volts. So your VDS is very much greater than your VGS. So what is the state of your transistor? VDS greater than VGS minus VTH. So your transistor is in saturation. So therefore now your current is going to be, now your current ID is going to vary. It is going to vary with your VGS. As VGS increases, your current also increases. So therefore what happens to Vout? Vout is VDD minus ID into RD. As ID is increasing, your Vout with this term increases. So when this term increases, you are subtracting this value, and the subtracting value is increasing. So therefore ultimately Vout is going to decrease. So your Vout decreases. So this continues till when this continues? This continues till the third situation occurs. What happens at the third situation is, as you are increasing the VGS, ID is increasing, so simultaneously the voltage drop is increasing. So this voltage drop increases, and your output voltage decreases. And after some time, after some point, you will encounter a situation where your VDS, this Vout value, becomes lesser than your Vin minus VTH. So let us assume this is 5 volts, and ID for this case ID was around 0.1 milli, and if I assume 1 kilo resistor, you will get 5 minus 0.1, 4.8. Here it was 4.8, and simultaneously that is by increasing this value, okay, I have at this stage I have come to a point where your VDD, where my ID has become equal to let us say my ID has become equal to 4 milliampere, and for my VGS minus VTH is equal to 1 volt. So what happens? Output voltage will be VDD minus 4 into 1. So 5 minus 4, 1 volt. That means your VDS will be 1 volt. This voltage will be 1 volt. Whereas your Vin minus VTH is also 1 volt. So therefore your Vout is equal to Vin minus VTH. If you further increase Vin minus VTH, what happens? Your Vout is going to become lesser, because this value is increasing. This 4 will increase to 4.5, let us assume. So 5 minus 4.5, 0.5. So 0.5 will become less than, suppose if you have increased by 0.1, 1.1. So therefore your transistor will enter into this region called as the triode region. So in triode region, it is going to act like a resistor. Therefore its GM is also going to vary with your output voltage. So here gradually it is going to fall. Therefore for a large signal, there are two limits to be considered. First is this limit, and other is this limit. Okay, if you use this amplifier, if you use this circuit for amplification of voltage between these two ranges, what is this range? This is let us call it as Vx. So between VTH and Vx, your circuit is going to behave like an amplifier, and out of this range, if you go out of this range, then you are going to get a clipping action, or you are not going to get an amplification. That is what happens. So from the last signal analysis, you will get the boundary conditions. So these are the boundary conditions you get for this circuit. What are the boundary conditions for MOSFET? That means common source amplifier. Boundary condition which we got was, first is your VGS should be greater than VTH. This is the first boundary condition. Second boundary condition is VGS minus VTH. This should be less than your Vout. What is Vout? VGS minus VTH should be less than Vout is VDD minus ID into RD. So whenever you design this circuit, so these are the two things. To calculate the gain, you can use the small signal result which we got for the gain, and to calculate this one minus GM into RD, and ultimately you have to take care that your circuit never goes out of these boundary conditions. Okay, so these are the boundary conditions which are defined for your amplifier. So here what we talked about was a very simple amplifier. We used RD here, whereas when you go for a fabrication, ICs don't have resistors. That means you cannot fabricate resistors so easily in the IC. So therefore, how to get a circuit which is very good how to get a common source amplifier circuit which is suited for fabrication. So for that purpose, what you can do is you can use replace that RD by a this is diode connected. It is called as a diode connected MOSFET. So when you connect, what is happening here is we are going to connect the gate and the drain of the MOSFET. So once you connect the gate and drain of the MOSFET, it is going to behave like a resistor. We will see how it behaves like a resistor. Okay. So the other remaining part remains the same. So here is your amplifying circuit. Vin you have applied here. Okay, instead of the resistor here, you have replaced that resistor with a diode current. So what is this actually? Okay, why we have connected here? So let us see by substituting the model of your MOSFET, small signal model of your MOSFET. Let us call this as an M2 transistor and M1 transistor. So this is model of M2 gate. This is GM2 VGS, and your MOSFET is going to have an output resistance R0, and this is going to be the output. Okay, this is drain, gate and source. What you have done in this case, you have connected the gate to the drain. That means this is my gate and this is drain. I am shorting them. Okay, so let us see what will be your Vout. Okay, so this Vout, first of all, what is VGS? VGS is the voltage between gate and source, VGS. So once you have connected gate to drain, so this output voltage is going to be this voltage as well. Okay. Why? Because everything is in parallel, so the voltage in a parallel circuit is going to remain the same. So Vout, your VGS will now be equal to your Vout, and even this is your Vout. So what is, let us calculate what is your Vout. So Vout will be given by, so this GM VGS gets replaced by GM into Vout. So this Vout is nothing but, if you assume this current to be flowing in this direction through this resistor, you are going to get the Vout. So that is minus GM into Vout. Okay, let us assume that there is a current flowing through this output node IX. So this current IX gets distributed between this current and the current through this R0. So Vout is given by, that means this total current IX will be given by this current GM2 into Vout plus the current through this R0 resistor. So what will be the current through this R0 resistor? R0 is having a voltage drop Vout across it, and value of R0 resistance is R0. So Vout by R0 is going to give you the current through it. So from this, Ix is going to be, Vout can be taken common, GM2 plus 1 by R0, or you can write V0 by Ix is equal to V0 divided by X is equal to 1 by GM2 plus 1 by R0. So this is going to give you V0 divided by Ix. This I will represent by a resistor Rx. So this will be given by R0 divided by GM2 into R0 plus 1, or I can write this as R0 into 1 by GM whole divided by R0 plus 1 by GM. This is R1 into R2 divided by R1 plus R2, which means it is R0 in parallel by 1 by GM2. So therefore your Rx output resistance, when seen through this terminal, it is going to be R0 in parallel with 1 by GM. But I have already said you R0 is a very huge value,